Arizam class, break time is over. Before break, we were talking about methods of accessing units of data. So we talked about the sequential access, where data is stored as a record and the access is done in a specific order, in a specific sequence. So there is no way you can access, for example, the data stored at memory location Fn before you get access to the previous memory location. So that means we have to get access to the data one after another in a specific sequence. Now, for direct access, we have to use a shared read memory mechanism. We have to use a read-write mechanism which allow data to be stored in blocks or records with a unique physical address. We have to store data at a specific memory location, using a specific memory address. Now, that means when the CPU wants to get access to the data, there is a way it can get access to a specific memory location without having to get access to the previous memory addresses. Now, you see that in the example that we have on the screen, we have a direct access to the element which is stored at the address memory location. Let's say the address number 4 in the list, which can be easily accessed without having to access to the element before the element number 4. So this means that the access time has to vary by location. It all depends by the location. Now, the next one is random access. For random access, each location also has a unique address, a unique word-in address. That means there is direct access to any location. There is direct access to any location, as you can see depicted by the picture on the screen. We have constant access time. That means it is not linked to any sequence of access. So we have this as a random access, which means each location has a unique word-in address, and there is a direct access to any location without having access to the previous location. Now, the next one, the next method of accessing unit of the data is the associative. The associative is a type of random access memory. This is a bit different from the previous one because it has to compare specific bit patterns within the words. Then it performs a comparison across all the words simultaneously at the same time. So the data needs to be retrieved. It has to retrieve a word of the data based on its content, not its address. This is very important. Now, the previous memory access unit of the data, including the sequential one, they access data using the memory addresses. The next one, the direct one, memory access, it also uses memory location. The random access also uses the memory location, but it is independent of the sequence. For associative memory access, it does allow the CPU to get access to the data using what we call content, not address. So this memory method of accessing unit of the data is a bit different from the previous ones, as it uses the content of the data to get access to the to retrieve data. It does not rely on the addresses. The next one is about memory performance. we're going to talk about some characteristics or some memory performance evaluation metrics. Now, from a user's perspective, there are two important memory characteristics that include the capacity. What is the capacity of the memory? This is very important. We needed to talk about the capacity of the memory. We needed to have a big size memory. And also there is the performance of the memory. The performance of the memory. How long does it take to retrieve the data from the memory? Or how long does it take to store the data to the memory? So the performance is very important. So we have to evaluate the memory performance using the three different parameters that we are going to learn. The first one is access time, latency. Access time. This is the time required to complete a read or a write operation. Now, access time, how long does it take to write data to the memory? Or how long does it take to retrieve the data stored from the memory? We call it memory access time. So for RAM, the time from address presentation to the data availability. Now, when the CPU provided the address, I needed the data from this memory location. This is for RAM. That is the time the RAM got the memory location, the memory addresses from the CPU, and the time the data will be available to the CPU. We call it the memory access time specifically for the random access memory. For no RAM, for volatile memory or for disk, we need the time to position the read or the write mechanism. So memory access time for random access memory is the time that the CPU, from the CPU provided the memory location to the time the memory retrieve the data or the memory store the data to the memory. For no volatile memory, for no random access memory, we have the time to position the read or the write mechanism. Now, the next one, we need to talk about memory cycle time. We have memory access time. This is the time it takes the memory to retrieve data from the memory, or this is the time the memory it takes to write data to the memory. For random access memory, it is the time from when the memory addresses is issued by the CPU and the time the data will be available. For memory cycle time, this is another memory performance factor, memory performance evaluation metrics. That is the access time, memory access time, plus some additional delays before the next access. Now, this includes, for example, some delays linked with signal stabilization or data regeneration. Now, for memory cycle time, we need memory cycle time, we need the memory access time, plus some delays. Delays linked with signal stabilization or delays which are more related to the bus system. If you still remember, to transit data, we need we use what? We use what? Data bus. So there are some delays linked with the process system. That's why we need also to talk about memory cycle time, not only memory access time. So we have these three important factors to help us evaluate the memory performance. We have transfer rate, we have access time, memory access time, we have memory cycle time, we have memory transfer rate, well, we have the speed at which data is being transferred to the memory or from memory. This is what we call transfer rate, a speed at which data is being transferred to the memory or is being transferred from the memory. So for a random access memory, this transfer rate is inversely proportional to the memory cycle time. It is the inverse of the memory cycle time. Now we have the Tn equals to Ta plus N divided by R. Well, Tn is average time to read the data or write n-bit data, to read or write n-bit data. We also have TA, which is the average access time. Average access time. And we have also the N, which is the number of bits. Number of bits that need to be written to the memory or read from the memory. Number of bits. We have also L, which is the transfer rate. Transfer rate is being expressed in bit per second. BPS. So this is the expression which can help us to find the memory transfer rate. We have a simple example here. A computer system which has the following memory specification. We have the memory access time, that is the TS, that is 120 nanoseconds. Then we have the memory transfer rate, R, which is 100 megabits per second. So we needed to find the average time required to read or write 200 bits of data. So we have average time to read data or write data to the memory for n bit. We have Tn equals to Ta. We have the Ta, which is 120 nanoseconds. That is the time, the average access time. We have also the n bit. The n bit, this is 200. And we have also the transfer rate, which is 100 megabits per second. So we can easily find the total number of the average time that is required to read these 200 bits of data. Are you there? Huh? Are you there? Huh? So what is the average time required to read 200 bits of data? Are you there? You are tired with your midterm exam? What is the average time required to read 200 bits? We have the formula there. We need to apply this formula. Hello, are you there? Huh? You need one more quiz? Or after midterm exam, no more quiz? So it's quite easy. We have the average access time, TA. This is 120 nanoseconds. Then we have the total number of bits. This is N. We have 200 bits. And we have memory transfer rate. That is R. We have 100 megabits per second. So we needed to find the average time which is required to read the data, which is 200 bits. So it's quite easy. You only need, we almost have everything. We have the TA. This is the average time to read 200 bits. We have the N. That is the 200 bits. We have the R, the transfer rate. That is 100. So the only thing that you need is to fill in the vary, then you get the average time that required to read or write 200 bits. The same goes for the average time required to read 1000 bits. You only need to fill in the vary. We have N, which is now equals to 1000. So you can easily find the answer. So the time which is required to read the 1000 bits, and the time which is required to read the 200 bits. So it's quite easy. Now, we're going to have a look at this memory hierarchy. If you still remember, we had a short view, a short summary of the memory hierarchy from the previous lecture. But in today's class, we have this big picture with more details. When we have the registers is on chip storage. That means we have registers which are integrated into our central processing units, registers on chip storage. And we have the next level of the memory, which is a cache memory. We have SLAM and multiple cache levels. We might have multiple cache levels. As I said, we can have level 1, level 2, level 3, up to level N, depending on the technology. Then we have the main memory. The main memory here is can be a type of DRAM memory. It can be a DRAM memory, or it can also be a SLAM memory, a DDR memory, or a synchronous DRAM. It all depends on technology. This is what we call in-board storage. So the first one, the registers and the multiple cache levels, we call them on-chip storage. Now, after the main memory, we need to store the data permanently. We have to get the second storage memory. Here we have solid state memory, and this might be a flash memory, SSD, or a flash drive. Then what's next? We have the virtual memory and file database memory. So we're going to learn more about the virtual memory. This time we don't need to worry about this. We're going to learn what is virtual memory, why is it very important in the computer system, how does it work. But now what is important is to understand at which level is our virtual memory. You see, it only comes after the secondary storage memory, the solid state memory. Then we have offline bulk memory, magnetic tape. So these are offline storage. Now we have on-chip storage, that is the registers and the different levels of cache memory. Then we have in-board storage, that is the main memory. And we have outboard storage, that includes the solid-state memory and the virtual memory. Then we have offline memory. Now, for each level I, we have a cost CI. That is the cost per byte. For each level I, we also have TI. That is the average access time. For each level, we also have RI. That is the average data transfer rate. So there is a typical relationship between a memory at level MI and the following memory level MI plus 1. Now, when it comes to the cost, now pay attention to this. It is very important. When it comes to the cost of a memory at level I has to be higher than the cost at a memory at level I plus 1. So this means what? In summary, higher level memory are more expensive per byte. Higher level memory are more expensive per byte. Now we have the register memory, which is more expensive, which is expensive to the cache memory, different levels of memory. And we have the cache memory, which is at a level I, and the main memory is at level I plus 1. That means the cache memory is more expensive than the main memory. Main memory, solid state memory. This is the level I, and this is the level I plus 1. Now, when it comes to average access time, the average access time, the higher level memories are faster. TI for the registers memory, we have the TI which has to be less if you compare the TI at a memory at level I plus 1. That means the speed, the average access time for register memory is less if you compare to the cache memory. The average access time for the cache memory, each level of the cache memory, is less if you compare to the average access time of the main memory. That means that, in summary, high level memory are faster. Now, let's talk about the typical relationship between a memory at level MI and a memory at the following level memory MI plus 1. Late average data transfer, we have the higher levels memory which have a higher transfer rates. Now, a memory at a level I, it has a higher level transfer rate if you compare the level of the transfer rate of the level MI plus 1 memory. Now, when it comes to the total memory size, SI, we have higher level memory which are smaller. Now, the register memory is smaller if you compare to the cache memory, and the cache memory is smaller if you compare to the main memory, and so on and so forth. So this is the memory hierarchy, but this time we have more details. We have to compare the memory levels in terms of the cost per byte, average access time, average data transfer rate, and the total memory size. Now, we have an example. This is an example of the memory hierarchy, IBM Z13. This is very important. We have on-chip memory. Hello, we have on-chip memory, on-chip storage memory. That is, we have level 1 cache. And if you try to see, we have 8 cores. We have 8 cores. This is call number 1. The call number 1 include level 1 cache memory for instruction. We have level 1 cache memory for data. Then we have level 2 cache memory for instruction. Then we have level 2 cache memory for data. This is the call number 1. We have the same for call number 2. We have instruction, level 1 for instruction. We have level 1 for data. And we have level 2 for instruction. And we have level 2 for... We have in total 8 cores. This is what we learned last time, is about merge cores. Merge cores, we have many cores on a single processor chip. Now we have level 3. Level 3 cache. Level 3 cache. So this is the PU chip. Now we have level 1 cache for instruction, level 1 cache for data, level 2 cache for instruction, level 2 for data for each core, up to 8 cores. So that means we have 8 cores. Now, specific data and specific instruction for each core, we can find them easily in level 1 and level 2 cache. When it comes to common data and instruction, for all the 8 cores, we found them in level 3 cache. We found it in level 3 cache. Now, hello? We have level 1 cache for instruction, level 1, 2 for instruction, level 1 for data, and the level 2 for instruction. This is for each core. We have 8 cores in total. So, specific data and instruction for each core, we can find them easily in level 1 or level 2. When it comes to the common data and instruction for all these 8 cores, they are stored in level 3 cache. So this is a common level cache for these 8 cores. Okay? Clear? This contains common data and instruction for these 8 cores, and these ones contain specific data and instructions for each core. This is very important because we're gonna talk about this in more details later on in this course. Now, we have level 1 cache for instruction, and level 1 cache for data. You see that for level 1 cache for instruction, what is its size? Its size is 96 KB, and it is a NESLAM type memory. We have level 1 instruction. That is a cache, level 1 cache instruction memory is 96 KB. Now we have level 1 data cache is bigger than the previous one, is 128 KB. They are all SLAM. They are all SLAM type memory. They are all SLAM type memory. And we have level 2 cache and level 2 data cache. The size for this one is 2 megabytes. This also is a 2 megabytes. They are also SLAM memory. Now, what does this mean? You see that from level 1 cache instruction to level 2 cache instruction, the size of the memory has been increased. Clear? Does this mean that the speed has been also increased? Hello? This means that the speed has been increased or decreased. Huh? The size of level 1 cache instruction was 96 KB. And the size of the level 2 instruction cache is now 2 MB. They are all SLAM type memory. So tell me, what is the speed of this compared to this one? Which one is fast? Which one is fast? Which one is fast and why? No why in the exam, no why in the quiz. Why? Which one is fast and why? From the memory hierarchy, which one is fast and why? Hmm? 29. Class 5, 29. Not 29. So which one is fast? From the memory hierarchy. As the size of the memory increase, we see here, they are all the same type, right? But you see the size here is 96 KB and here is 2 MB. So they are all cache memory, but this is level 2 and this is level 1. So which one is fast? Two? Why? Which one is bigger? This one is smaller than this. Which one is bigger? Two. Which one is fast? One. As the size of the memory increases, the speed decreases. So this is very important. That's why I want everybody's attention. This is very important. So here we have a big size, but small speed. Now here, we need also to know level 3 cache. Level 3 cache is 64. 64 MB and it is ED lam. ED lam in this case. Now here, you see that we have a big site for level 3 cache, and this level 3 cache is to store common data for these 8 cores. Common data and instruction for these 80 cores needs to be found in the level 3 cache as it is depicted by the memory organization that we do have here on the screen. Now, the next one, we have level 4 cache. Now, level 4 cache is 480 MB, and it is a needy lam. Now, for level 4 cache, we have one node which contains 3 PU chips. We have seen here one PU chip. So these nodes will contain 3 PU chips. And we have 2 nodes per drawer. So we have 2 nodes per drawer up to the 8th node. So that means we have 4 different drawers. We have 4 different drawers. And we have the central processing complex. Now, since we have 2 nodes per drawers, and we have 8 nodes, in total we have 4 drawers. Now, after the level 4 cache, we have the main memory. We have the main memory. The main memory here is 2.5 terabytes. We have 2.5 terabytes for the main memory. And this is only per drawer. 2.5 terabytes per drawer. Now, since we have 4 different drawers, we have seen that each node contains up to 3 PU chips and 2 nodes per drawers. And since we have 8 nodes, that means we have 4 drawers. And we have a main memory, which is a physical memory, which is a 2.5 terabyte per each drawer. That means in total we have 10 TB for the CPC, for the central processing complex. So this means since we have 4 drawers, we have 2.5 times 4. That means we have 10 TB per what we call CPC, the central processing complex. Now, after we have a secondary storage. We have a secondary storage memory. This can be a virtual memory. You can have a virtual memory. And it can be on disk array or storage network. So this is what we talked about an example of memory hierarchy. It is IBM D13. So make sure you do understand more about this memory hierarchy, and specifically for this example, you may expect some questions related to the memory hierarchy, and this is very important in the computer system. We needed to understand the different levels of memory. We needed to understand their speed. We need also to understand the cost. We need to understand the density. We needed to understand when we can find specific data for a specific call. We need also to find where we can find the specific instruction for a specific call. We need also to find where are the common data and instruction for the whole in whole system environment. Questions about this memory example of memory hierarchy? Questions? Now the next one is the design principle for a memory hierarchy. We talked about the advantages of the memory locality. We talked about the memory locality, temporal, and spatial. Now, we're going to have three principles that can guide memory hierarchy design and is supporting hardware. So this is locality. We have to enable effective use of memory hierarchy, programs that tend to access a small or a localized set of data instruction at a time. We have inclusion or initial data stored in the at a lowest level, that is MN. High-level memory store the subset of the lower level. So we have data that need to be moved upward during the processing. That is from MN level up to MN-1 level, MN-2 level, and so on and so forth. So it has to be expressed as MI has to be less than and equals to MI plus 1. So we needed to talk about covalence, cache covalence. This has to be very important when considering the cache memory or the different levels of memory. We have to copy the same data in two different memory levels. So these need to have to be consistent to make sure that we have updated data in the memory system. That means a copy of the same data in different memory location, in the different memory levels, needed to be consistent. Do not have different data, different data at the same memory levels. So copy of the same data in different memory levels needed to be consistent. If there is any update at any memory levels, the update needs to be taken into consideration in other memory levels to make sure that we have consistency about the same data in different memory levels. So that means that if there is any data which is modified in any level, let's say in level 1 cache, and the same data exists in level 2 cache, that means the level 2 cache also needed to be updated about the change of the data in data. So updates need to be immediately, all eventually across all the higher memory levels. So memory covalence is very important. Needed to make sure that the same data, the copy of the same data in different memory levels have to be consistent. It has to be consistent. All right. Questions? We have this picture that depicts relative cost, size, and the speed. As I talked before, we have the x-axis and the y-axis. The x-axis depicts increase in access time and increase in size. As the size increase, there is increase in access time, and the y-axis depicts the increase in cost per GB and the increase in the transfer rate. So you see, this is the relative cost, size, and speed characteristics for our memory system. All right, so that's it for today's class. If there is no question, up to next time, take care. I'll see you next time. Have a nice holiday.